Hello, and welcome back to Sleep Science Chronicles. Whether you are tucked beneath your covers at the end of a long day, resting your eyes in a quiet room, or simply looking for a calm place to let your thoughts settle, you have found the right place. Tonight, there is no rush. There is nowhere you need to be. There is nothing you need to do. Just breathe. Settle into whatever position feels most comfortable, and let yourself be carried gently forward by the sound of these words. Tonight, we are going to spend some time with something extraordinary. Something so slow, so patient, so quietly immense that it makes everything in human experience feel like the blink of an eye. We are going to talk about how stars are born. Not the dramatic version you might imagine. Not an explosion, not a sudden flash of light. The truth is far stranger and far more beautiful than that. A star is born through a process so unhurried that it can take 10 million years, 50 million years, sometimes longer. A process that begins in silence, in cold, in utter darkness, and unfolds with a patience that no human word quite captures. We will wander through the enormous clouds of gas where this process begins. We will sit with the numbers that describe how long each stage takes. We will visit real places in our galaxy where stars are forming right now, at this very moment, though no one alive today will see them finish. And along the way, we will discover that the slowness is not an obstacle to the story. The slowness is the story. Some of these facts will be gentle and quiet. Others may stretch your sense of time in ways that feel almost dreamlike. All of them are true, and all of them are waiting for you, in no hurry at all. If these calm explorations help you unwind at the end of the day, a gentle like or a quiet tap on subscribe helps other sleepy souls find their way here too. One sleepy soul at a time. That is how we grow. Now let us begin. The scale of slowness. Setting the stage. The fastest event a human being can perceive is a flash of light lasting about 13 milliseconds. 1/13th of a second. That is the floor of our experience. Anything faster than that, and our brains simply cannot register it as a separate moment. On the other end, the longest event most of us will ever witness from start to finish is the slow turning of a season, roughly 3 months of gradual change from one state to another. Star formation operates on an entirely different clock. The collapse of a molecular cloud into a fully formed, hydrogen-fusing star takes, at minimum, roughly 10 million years. For smaller stars, the kind that burn cool and red and faint, the process can stretch beyond 100 million years. These are not estimates rounded up for dramatic effect. They are the actual measured timescales that physics demands. To begin to sit with what 10 million years means, consider this. If you compress the entire formation of a sun-like star into a single calendar year, from January 1st to December 31st, then the entirety of recorded human civilization, every empire, every war, every poem, every song, would occupy the final half-second before midnight on New Year's Eve. Not the final day, not the final hour, the final half-second. The age of the dinosaurs, all 165 million years of it, would represent roughly 16 and a half calendar years on that same scale. The dinosaurs lived and died across an interval that would be 16 times longer than our compressed star formation year. And yet even the reign of the dinosaurs is brief compared to the time it takes the smallest stars to finish forming. Some red dwarfs take so long to coalesce that the dinosaurs could have risen and gone extinct 5 or 6 times over before the star completed its birth. If you were somehow able to watch a molecular cloud begin its collapse and then fast forward through time at a rate of 1,000 years per second, you would still need to sit and wait for nearly 3 hours before a sun-like star ignited its core. 3 hours of watching at 1,000 years per second. The slowness is not a detail of the process. It is the defining feature. Human D's life unfolds over decades. Geological change unfolds over millions of years. But star formation sits at the intersection of these two timescales in a way that makes it uniquely difficult for our minds to grasp. It is fast enough that, in cosmic terms, it happens all the time. Stars are being born constantly across the galaxy right now. And yet it is slow enough that no human being, no civilization, no species has ever witnessed the full arc of a single star's birth from beginning to end. The light from the Orion Nebula, one of the most active stellar nurseries visible from Earth, left that cloud roughly 1,340 years ago. In the time since that light began its journey, the protostars forming inside the nebula have barely changed at all. 1,000 years for them is a single breath in a process that will take millions more. There is something calming in that thought. In a world that often feels as though everything moves too quickly, star formation is a reminder that the universe has no such anxiety. It builds its most magnificent creations at a pace so slow it might as well be stillness. And it does so without any hurry at all. The fastest stars to form, the massive, brilliant blue giants, still take at least a few 100,000 years to finish the process. A few 100,000 years is their version of rushing. These are the impatient ones, and even they would outlast every human structure, every written language, every archaeological trace of our species. When astronomers study star-forming regions, they do not watch stars being born. They cannot. Instead, they take snapshots, images of clouds at different stages of collapse, and piece together the sequence the way a biologist might reconstruct the life cycle of a tree by photographing many different trees at different ages. No single astronomer will ever follow one protostar from its first shiver of collapse to its first moment of fusion. The process is too slow for any career, any institution, any civilization. And perhaps that is part of what makes it so remarkable. Star formation is an act of creation that no conscious mind has ever witnessed in full. Every star you have ever seen in the night sky completed its birth in private across an interval so vast that no observer could have stayed awake for the whole thing. The stars formed in silence and in patience, and by the time anyone was around to notice them, they were already burning as though they had been there forever. The raw material, molecular clouds. The birthplace of every star in the universe is a molecular cloud. These are among the largest structures in any galaxy. Vast, cold, diffuse expanses of gas and dust that drift through interstellar space like fog banks stretching across light years. A typical molecular cloud can span 100 light years or more. That means a beam of light traveling at 300,000 kilometers per second would need a full century to cross from one side to the other. Despite their immense size, molecular clouds are almost unimaginably sparse. The densest regions of a typical cloud contain roughly 10,000 molecules per cubic centimeter. That sounds like a lot until you compare it to the air in the room around you right now, which contains approximately 25 quintillion molecules in the same volume. The densest part of a molecular cloud is a better vacuum than anything humans have ever created in a laboratory. If you could somehow stand inside one, you would see nothing, feel nothing, and detect nothing without instruments. The temperature inside a molecular cloud hovers around 10 to 20 Kelvin. That is 10 to 20 degrees above absolute zero, the lowest temperature physically possible. At these temperatures, atoms move so slowly that they barely vibrate. Molecules of hydrogen cling together in pairs, forming the H2 that gives molecular clouds their name. It is a stillness so deep that the very particles of matter seem to be holding their breath. Most of the mass of a molecular cloud is hydrogen, roughly 73% by weight. Another 25% is helium. The remaining 2%, a tiny fraction, contains every other element: carbon, oxygen, nitrogen, silicon, iron, and traces of dozens more. That 2% is the legacy of stars that lived and died before this cloud existed. Every atom of carbon in a molecular cloud was forged in the core of an earlier star. Every grain of dust is a fragment of a previous generation's death. The dust grains inside a molecular cloud are extraordinarily small, typically less than 1 micrometer across, smaller than a bacterium. Yet they play a crucial role in star formation. Dust grains block light from passing through the cloud, creating the dark patches visible in photographs of the Milky Way. Those inky voids in the star field are not empty spaces. They are molecular clouds so thick with dust that the stars behind them are completely hidden. Some molecular clouds are enormous. The Orion Molecular Cloud Complex, which contains the famous Orion Nebula, stretches across hundreds of light years and contains enough gas to form tens of thousands of stars. The molecular cloud complex in the constellation Taurus is quieter and more diffuse, forming stars at a much gentler pace, mostly small, cool ones that will burn for trillions of years. Each cloud has its own character, its own pace, its own preferences for the kinds of stars it tends to produce. A single molecular cloud can contain enough raw material to build anywhere from a few dozen to several million stars. The Milky Way contains several thousand molecular clouds of various sizes, and new ones are still forming as gas cools and collects in the galaxy's spiral arms. The raw material is everywhere. The patience required to turn it into a star is what makes the process so extraordinary. Inside these clouds, there are regions of slightly higher density called clumps. Within the clumps, there are even denser pockets called cores. A dense core might be only a fraction of a light year across, small by cloud standards, but it contains enough concentrated gas to eventually collapse into a single star or a small group of stars. These cores are the seeds. They sit inside their parent clouds for hundreds of thousands of years, sometimes millions, before anything happens. They are waiting, though not for anything in particular. They are waiting for the balance to tip. Every molecular cloud exists in a state of delicate tension. Gravity pulls the gas inward, trying to collapse it. Thermal pressure, the tiny residual motion of molecules, even at 10 Kelvin, pushes outward, resisting collapse. Magnetic fields thread through the cloud, providing additional support. And turbulence, chaotic, swirling currents of gas, stirs the cloud constantly, preventing it from settling into a smooth, collapsible state. For a cloud to begin forming stars, something must disturb this balance. Something must give gravity the upper hand. That disturbance might come from outside, a shock wave from a nearby supernova, the gravitational squeeze of a passing spiral arm, or the collision of two clouds drifting through the galaxy on slightly different paths. Or it might come from within, a region of the cloud that happens to be just dense enough, just cold enough, just quiet enough for gravity to begin its work. However it begins, once the balance tips, the process is irreversible. Gravity has no off switch. Once a dense core begins to collapse, it will continue to collapse until something stops it. And the only thing capable of stopping it is the ignition of nuclear fusion at the core of a new star. That ignition lies millions of years in the future. The collapse has only just begun. The gas at the center of a collapsing core falls inward at roughly 1/10 of a kilometer per second. That is about the speed of a person jogging. At this pace, it will take approximately 100,000 years for the innermost material to reach the center. 100,000 years of falling at jogging speed through nearly perfect darkness, in nearly perfect silence, and nearly perfect cold. There is no drama in this stage. There is only falling and waiting. And so the cloud waits. The core waits. The gas waits. Everything in this story waits. Because waiting is what star formation is. It is the universe demonstrating that the most extraordinary things are not built in moments of urgency, but in epochs of quiet, unbroken patience. The first collapse. Gravity's patient work. When a dense core inside a molecular cloud finally begins to collapse, the event is so gentle that nothing in the surrounding cloud would notice. There is no sound, there is no flash, there is no shock wave. The gas at the center of the core simply begins to drift inward, drawn by the accumulated gravitational pull of every other particle around it. The collapse begins at speeds so low that it would be entirely invisible to any instrument we currently possess if it were happening at the distance of the nearest molecular cloud. The initial phase of collapse is called free-fall collapse, though the name is somewhat misleading. It conjures images of rapid plummeting, but in the context of a molecular cloud, free fall means something different. It means the gas is falling under gravity alone, with no other force significantly opposing it. And because the gas is so diffuse, so spread out across such enormous distances, the free fall timescale is immensely long. For a typical dense core with a mass similar to our Sun, the free fall time is roughly 100,000 years. That is the time it would take for the gas to collapse from a diffuse cloud into a concentrated central object if nothing slowed it down. In practice, the process takes even longer because thermal pressure, magnetic fields, and residual turbulence all resist the infall to varying degrees. The true collapse timescale for a Sun-like star is closer to several 100,000 years for the initial concentration phase and millions of years for the full journey to a stable, fusing star. During this initial collapse, something remarkable happens to the temperature. For a long time, tens of thousands of years, the collapsing gas barely warms up at all. This seems counterintuitive. When you compress gas in a bicycle pump, it heats up almost instantly. But in a molecular cloud, the gas is so thin and so transparent to certain wavelengths of radiation that any heat generated by compression is immediately radiated away into space. The collapsing core glows faintly in the far infrared, shedding its heat as fast as gravity adds it. The temperature stays near 10 Kelvin. The collapse proceeds in cold and darkness. This phase is sometimes called isothermal collapse, collapse at constant temperature. It is a peculiar and beautiful stage because the gas is falling inward, gaining energy from gravity, and yet remaining cold. The energy does not disappear. It is converted into infrared photons that stream outward through the cloud and into interstellar space, carrying the heat away at the speed of light. The collapsing core is, in a sense, refrigerating itself as it contracts. The isothermal phase cannot last forever. As the gas at the center of the core grows denser, it eventually becomes opaque, thick enough that infrared photons can no longer escape freely. When this happens, the heat generated by compression begins to build up. The temperature at the center starts to rise, slowly at first, then more steadily. This transition occurs when the central density reaches roughly 10 billion molecules per cubic centimeter, 1,000,000 times denser than the original cloud, but still far less dense than the air you are breathing. The moment the center becomes opaque and begins to warm is a quiet turning point. It means the collapsing gas can no longer shed its heat. From this point forward, every bit of gravitational energy converted into thermal energy stays trapped at the center, building pressure, raising the temperature, gradually creating the conditions that will, millions of years from now, ignite nuclear fusion. But that moment is still impossibly far away. The center has warmed from 10 Kelvin to perhaps a few hundred Kelvin. It needs to reach 10 million Kelvin before hydrogen can fuse. The gap between a few 110 million is staggering, and crossing it will take the bulk of the star's formation time. The gas continues to fall. Layer upon layer accumulates at the center, each new arrival adding its weight, its pressure, its heat. The process is sometimes compared to building a snowball by letting snowflakes fall onto a single point, one by one, over millions of years. The comparison is apt in its slowness, but fails to capture the scale. The snowball being built at the center of this collapsing core will eventually contain a mass equal to 330,000 Earths. During this early collapse, the surrounding molecular cloud carries on as if nothing is happening. Stars elsewhere in the cloud may already be burning. Other cores may be collapsing on their own schedules. The cloud is large enough and diffuse enough that events at one core have little effect on cores elsewhere. Each collapsing region exists in its own quiet bubble of slow motion change. The outer layers of the collapsing core are still falling inward, but they are falling onto a center that is now growing hotter and denser by the millennium. As the center warms, it begins to exert outward pressure, not enough to halt the collapse, not yet, but enough to slow it. The infall rate, already glacial, becomes even slower. The gas approaching the center must now push against a growing cushion of thermal pressure. This tug of war between gravity pulling inward and thermal pressure pushing outward will define the next several million years. Gravity will win, ultimately, because more mass keeps falling from the outer envelope, adding to the central object's gravitational pull. But the victory is not swift. It is ground out over eons, one thin layer of gas at a time. If you could somehow place a clock at the center of this collapsing core, you would watch the temperature rise by perhaps 1 degree every few thousand years during the early stages. Later, as the mass accumulates and the pressures grow, the temperature would climb faster. Perhaps 1 degree every few centuries, then every few decades, but even at its fastest, the warming would be imperceptible on any human timescale. You could watch for your entire life and see no change. Gravity does not rush. Gravity does not rest. It simply pulls constantly, uniformly, without urgency, without pause. And in its quiet, ceaseless work, it builds something that will one day outshine everything around it, but not today. Not for millions of years. For now, there is only the falling and the warming and the waiting, the dark phase, before any light. For a remarkable stretch of its formation, a developing star produces no visible light at all. None. The collapsing core is too cool to glow in any wavelength that human eyes could detect. It radiates only in the far infrared and sub-millimeter. Wavelengths so long that they are invisible not just to our eyes, but to most optical telescopes as well. For tens of thousands of years, the forming star is a dark object growing silently inside a dark cloud. Astronomers call these objects starless cores when they have not yet begun to collapse, and prestellar cores once the collapse is underway but before a central concentration has formed. The terminology is clinical, but the reality is poetic. A prestellar core is a place where a star already exists in potential, where gravity has already committed to building something, but where nothing yet shines. It is a promise being kept in total darkness. The darkness is not empty. Inside a prestellar core, molecules of hydrogen, carbon monoxide, ammonia, and dozens of other compounds drift and tumble in slow, cold currents. The gas moves at roughly 1/10 of a kilometer per second, about the speed of a brisk walk. At this pace, a molecule at the edge of the core would take tens of thousands of years to reach the center. There is motion, but it is the kind of motion that looks, on any human timescale, like perfect stillness. These dark cores are among the coldest places in the known universe. The temperature at the center of a prestellar core can drop to as low as 6 or 7 Kelvin, barely above absolute zero. At these temperatures, even molecules begin to freeze. Carbon monoxide, one of the most common molecules in interstellar space, freezes onto the surfaces of dust grains at temperatures below about 20 Kelvin, forming thin, icy mantles. Nitrogen-bearing molecules do the same. The chemistry of the core slows to a crawl as its ingredients literally frost over. This freeze-out, as astronomers call it, has a paradoxical effect. By removing molecules from the gas, it reduces the thermal pressure slightly, making it easier for gravity to continue the collapse. The cold itself aids the process of star formation. The colder the core gets, the less resistance it offers to gravity, and the more inevitable its collapse becomes. Cold is not the enemy of star birth. Cold is its ally. During the dark phase, the only way astronomers can detect these collapsing cores is by the shadow they cast. A prestellar core is visible in infrared surveys as a dark silhouette against the faint background glow of the galaxy. It absorbs and blocks the light of more distant stars, revealing its presence as an absence, a patch of deeper darkness in an already dark sky. Some of the most famous images of star-forming regions show these dark globules, small, inky shapes that look like holes in the star field, but are, in fact, the cocoons of future stars. The Barnard objects are a well-known catalog of these dark clouds and globules. Barnard 68, a nearly perfect sphere of cold, dense gas about 500 light-years from Earth, is one of the most studied. It is so opaque that essentially no background stars are visible through its center. Infrared observations reveal that Barnard 68 is on the verge of collapse. It may already be forming a star inside its lightless interior. But even if it has begun, the star it is building will not be visible for hundreds of thousands of years. Some prestellar cores have been collapsing for so long that they have begun to warm slightly at their centers, rising from 10 Kelvin to perhaps 15 or 20. This modest warming is enough to produce a faint glow in the far infrared, detectable only by space telescopes like the Herschel Space Observatory, which operated at wavelengths between 55 and 670 micrometers. Herschel cataloged thousands of these faint, cold sources in nearby molecular clouds, each one a star in the earliest, recognizable stage of its birth. Even with Herschel's sensitivity, many of these objects are so faint and so cold that they blend into the background. The dark phase of star formation is, by definition, the hardest to observe. It is the stage we know the least about, because the forming star is doing everything it can, inadvertently, to remain hidden. It does not yet glow. It does not yet emit jets. It does not yet clear its surroundings. It simply sits and collapses and waits. The dark phase can last anywhere from 50,000 to several 100,000 years, depending on the mass of the forming star and the conditions of the surrounding cloud. For the cores that will become low-mass stars, red dwarfs, orange dwarfs, stars even smaller and cooler than our sun, the dark phase is especially prolonged. These cores collapse more slowly because their gravity is weaker, and the thermal pressure, even at 10 Kelvin, is a more significant obstacle. A red dwarf might spend 500,000 years in complete darkness before producing any detectable radiation at all. During all of this time, the universe around the forming star continues as normal. Light from distant galaxies passes through the cloud. Cosmic rays zip through the gas, occasionally ionizing a hydrogen molecule. The magnetic field threading the core shifts imperceptibly as the gas rearranges. Nothing dramatic happens, nothing visible changes. And yet, inside this quiet darkness, something is being built that will eventually burn for trillions of years. There is something deeply restful about this phase. The universe does not require light to do its most important work. The most consequential act of creation in any galaxy, the birth of a star, begins in darkness so complete that even the universe itself can barely see it. And the darkness does not mean absence, it means patience. It means a process so gradual that it does not yet need to announce itself. The light will come. But first, there must be this long, quiet, necessary dark. Protostars, the first glow. After tens of thousands of years of silent collapse, the center of the forming star finally reaches a milestone. The accumulated gas has grown dense enough and warm enough to become what astronomers call a protostar, a hot, luminous core still buried deep inside its natal envelope of gas and dust, still growing, still accreting, but now unmistakably different from the cold cloud it emerged from. The protostar is not yet a star. It cannot fuse hydrogen, but it glows. The glow comes not from nuclear reactions, but from gravity. As gas falls onto the protostar's surface, it strikes at tremendous speeds, several kilometers per second, and the kinetic energy of that impact is converted into heat. The surface of a young protostar can reach temperatures of 2,000 to 3,000 Kelvin, hot enough to radiate in the infrared. It is a dim, deep, ruddy glow, invisible to the naked eye, but brilliant to an infrared telescope. This stage is classified by astronomers using a system of numbered classes. A Class 0 protostar is the youngest, deeply embedded in its envelope, invisible at optical wavelengths, detectable only in the far infrared and submillimeter. Most of its final mass has not yet fallen onto the central object. It is, in a sense, more envelope than star. The envelope outweighs the protostar at its center by a factor of 10 or more. A Class 0 protostar is so young that it has typically existed for fewer than 30,000 years. In the context of star formation, this is infancy, the first breath, the first heartbeat. And yet 30,000 years is longer than the entirety of recorded human history. The youngest recognizable stage of star formation has already outlasted every civilization our species has ever built. The transition from Class 0 to Class 1 occurs as the protostar accretes more of its envelope. A Class 1 protostar has gathered a significant fraction of its final mass, but it is still surrounded by a thick cocoon of gas and dust. It is brighter in the infrared, warmer and more structured. By this stage, a flattened disk of material has formed around the protostar, and the beginnings of bipolar jets may be visible. The Class 1 phase lasts roughly 200,000 years. The luminosity of a protostar is deceptive. A young protostar can be surprisingly bright, sometimes tens or even hundreds of times the luminosity of our current sun. But almost all of that light is in the infrared, and almost all of it is absorbed and re-radiated by the surrounding dust before it escapes the cloud. If you could strip away the envelope and see the protostar directly, it would be a swollen, glowing orb, far larger than the star it will eventually become. Protostars are bloated because they have not yet contracted to their final size. Gravity is still squeezing them, and that squeezing will continue for millions of years. The surface of a protostar is not a calm place. Material rains down unevenly from the surrounding disk. Magnetic field lines thread through the gas, channeling streams of infalling material along specific paths. Hotspots form where the accretion streams strike the surface, creating localized regions of extreme temperature that flicker and vary. The protostar's brightness can change significantly over timescales of months or years, a phenomenon astronomers call accretion variability. In rare cases, a protostar can experience an accretion burst, a sudden increase in the rate at which material falls onto its surface. These bursts can increase the protostar's luminosity by a factor of 100 or more over the course of just a few years. The most famous example is F.U. Orionis, a young star in the constellation Orion that brightened dramatically in 1936 and has remained bright ever since. F.U. Orionis events, as they are now called, are thought to occur when instabilities in the accretion disk dump a large mass of material onto the protostar in a short period. Even during an F.U. Orionis event, one of the most dramatic things a protostar can do, the timescales are slow by human standards. The brightening takes months to years. The elevated state persists for decades to centuries. The underlying formation process continues uninterrupted, as oblivious to the outburst as a glacier is to a summer rainstorm. The burst is a hiccup in a process measured in millions of years. Between bursts, the protostar grows steadily. Gas spirals inward through the disk, losing angular momentum through friction and magnetic interactions, and eventually crosses the inner edge of the disk to join the protostar. The growth rate varies, but for a Sun-like protostar, it is typically around 1/1,000,000th of a solar mass per year. At that rate, building a star with the mass of our Sun would take roughly 1,000,000 years. And indeed, that is approximately how long the main accretion phase lasts, about 1 to 2 million years of steady, patient accumulation. During this entire time, the protostar is invisible in ordinary light. The envelope of gas and dust surrounding it is so thick that optical photons cannot escape. The only way to see a protostar is to look at wavelengths long enough to penetrate the dust: infrared, submillimeter, and radio. It was not until the development of infrared astronomy in the 1960s and 1970s that protostars were observed directly for the first time. Before that, their existence was theoretical, predicted by the physics of gravitational collapse, but never confirmed by observation. The Spitzer Space Telescope, launched in 2003, transformed our understanding of protostars by surveying nearby star-forming regions in the infrared with unprecedented sensitivity. Spitzer cataloged thousands of protostars in clouds like Orion, Taurus, Ophiuchus, and Serpens, revealing the full range of protostellar stages for the first time. Each dot of infrared light in those surveys represented an object that had been collapsing for somewhere between 10,000 and several million years, a snapshot of patience caught in the act. More recently, the James Webb Space Telescope has pushed even deeper into the dusty envelopes of protostars, resolving structures that Spitzer could only hint at. JWST's images of the Orion Nebula revealed dozens of protostars at various stages, some still deeply embedded, others just beginning to clear their surroundings. Each one exists at a different point along a timeline that stretches across millions of years, and each one is completely unaware that it is being watched. The protostellar phase is sometimes described as the star's gestation period, the time between the first recognizable concentration and the moment when the star can sustain itself through nuclear fusion. The analogy is apt in its sense of slow development toward a threshold, but it misleads in one important way. A mammalian gestation has a fixed endpoint. Birth occurs when the organism is ready. A protostar has no such clear boundary. It grows and contracts and warms gradually, and the transition from forming to formed is a slow dissolve rather than a sharp moment. And so the protostar continues, growing, warming, brightening in the infrared, hidden inside its dusty cocoon. Millions of years pass, the envelope thins, the disk feeds, the center heats. Nothing hurries, nothing needs to. Accretion disks and jets, the architecture of birth, As a collapsing cloud core concentrates into a protostar, something beautiful and inevitable happens. The gas does not fall straight inward, because the original cloud possessed even a tiny amount of rotation, and virtually all clouds do, inherited from the turbulent motions of the galaxy. The infalling material begins to spiral. Conservation of angular momentum, one of the most fundamental principles in physics, ensures that as the gas moves inward, it spins faster and faster. The result is a flattened, rotating structure surrounding the protostar, an accretion disk. Protostellar accretion disks are large. A typical disk around a young sun-like protostar extends outward to roughly 100 astronomical units, 100 times the distance from the Earth to the Sun. That is more than 3 times the distance from the Sun to Neptune. If you could see one from above, it would look like a vast, slowly rotating platter of gas and dust, glowing faintly in the infrared, thickest at its inner edge, and thinning gradually toward its outer rim. The disk is not uniform. Its inner regions closest to the protostar are hot, reaching temperatures of 1,000 Kelvin or more. Its outer regions are cold, sometimes as low as 20 or 30 Kelvin, barely warmer than the original molecular cloud. Between these extremes, the temperature drops smoothly with distance, creating a gradient of conditions that will eventually determine what kind of planets, if any, can form within the disk. Material in the disk spirals inward toward the protostar, but it does so slowly. The journey from the outer edge of the disk to the inner edge can take tens of thousands of years. Gas at 100 astronomical units moves inward at a pace that would be almost imperceptible even on a scale of centuries. The disk is not draining rapidly into the star. It is feeding it gradually, like a slow drip from an enormous reservoir. The mechanism that allows gas to spiral inward is friction, or more precisely, viscosity. As neighboring rings of gas in the disk orbit at slightly different speeds, they rub against each other, transferring angular momentum outward and allowing the inner material to drift closer to the protostar. The exact nature of this viscosity was a mystery for decades, but it is now thought to arise largely from magnetic turbulence, a process called the magneto-rotational instability, first described by Stephen Balbus and John Hawley in 1991. This instability causes the magnetic field lines threading the disk to tangle and snap, creating chaotic, turbulent motions that act like an effective viscosity, slowly transporting angular momentum outward and mass inward. The disk is not just a pathway for gas to reach the star, it is also the birthplace of planets. Dust grains within the disk collide and stick together, gradually building larger and larger aggregates over hundreds of thousands to millions of years. These aggregates eventually grow into planetesimals, kilometer-sized bodies, and then into protoplanets. The entire planetary system forms within the disk, while the star itself is still forming. Star and planets are built simultaneously, from the same material on the same slow time scale. But the disk has another feature, one of the most visually spectacular phenomena in all of astrophysics. From the poles of the protostar, narrow beams of gas shoot outward at speeds of 100 to several hundred kilometers per second. These are protostellar jets, and they extend for light years in either direction, punching through the surrounding molecular cloud and creating glowing shock fronts where they collide with the ambient gas. The jets are powered by the interaction between the protostar's magnetic field and the inner edge of the accretion disk. As gas spirals inward and meets the protostar's magnetic field lines, a fraction of it is redirected and launched outward along the poles at tremendous speed. The exact mechanism is still debated, but the leading models involve magnetic centrifugal forces. The magnetic field lines act like slingshots, flinging gas outward along the rotation axis. The jets serve a crucial purpose. They carry away angular momentum that would otherwise prevent the gas from reaching the protostar. Without jets, the spinning gas in the inner disk would spin too fast to fall onto the star, and accretion would stall. The jets are the release valve that allows the star to continue growing. They are not a byproduct of star formation. They are a necessary component of it. Herbig-Haro objects are the visible manifestations of protostellar jets. Named after astronomers George Herbig and Guillermo Haro, who first cataloged them in the 1950s, these are small, bright nebulae created where the jets collide with surrounding gas. Herbig-Haro objects glow in the light of ionized hydrogen, sulfur, and oxygen, creating colorful, knotted structures that change visibly over timescales of years to decades. They are among the few features of star formation that change fast enough for astronomers to watch in real time. HH 46/47, located in a dark cloud in the constellation Vela, is one of the most studied Herbig-Haro objects. Its jets extend for nearly a light year in either direction, and JWST has imaged them in stunning infrared detail, revealing intricate shock structures and previously unseen knots of emission deep inside the cloud. The central protostar powering these jets is still deeply embedded, invisible in optical light, but its jets have punched clear through the cloud, announcing its presence to the universe, even as the star itself remains hidden. The jet phase lasts roughly as long as the main accretion phase, 1 to a few million years. As the protostar finishes gathering its mass, the accretion rate drops, the jets weaken, and eventually they shut off entirely. The disk thins and begins to dissipate, either accreted onto the star, blown away by stellar radiation, or incorporated into forming planets. What remains is a young star surrounded by a debris disk, the leftovers of a construction project that took millions of years to complete. The architecture of star birth, disk and jets, infall and outflow, is not optional. It is the universal blueprint. Every sun-like star in the galaxy formed with a disk. Every protostar that accreted significantly launched jets. The geometry is dictated by physics. Angular momentum demands a disk, and the disk's interaction with the magnetic field demands jets. It is the same process everywhere, in every molecular cloud, in every galaxy, repeated billions upon billions of times across cosmic history. And every time, it takes millions of years. T Tauri stars, the turbulent youth. After a few million years of accretion, the protostar has gathered most of its final mass. The thick envelope of gas that once hid it from view has thinned and dispersed, either accreted onto the star, blown away by jets, or swept up by stellar winds. For the first time, the young star becomes visible in optical light. It has emerged from its cocoon. Astronomers call these objects T Tauri stars, named after the first one identified. T Tauri, a variable star in the constellation Taurus, recognized as a young stellar object in the 1940s. T Tauri stars are not yet true stars in the strictest sense. They have not yet ignited stable hydrogen fusion in their cores. Their luminosity comes primarily from gravitational contraction, the slow shrinking of the star under its own weight, which converts gravitational energy into heat and light. They are essentially still collapsing, just very slowly, and they will continue to do so for millions of years until their cores reach the 10 million Kelvin threshold needed for hydrogen fusion. The T Tauri phase is the longest visible pre-main sequence stage. For a star with the mass of our Sun, it lasts roughly 10 to 30 million years. For lower mass stars, it lasts even longer, up to 100 million years for the smallest red dwarfs. During this entire time, the star is visible, bright, often brighter than it will be as an adult, and deeply unstable. T Tauri stars are among the most variable objects in the sky. Their brightness can change by a full magnitude or more over timescales of days to weeks. This variability comes from several sources. Hot spots on the stellar surface, created where gas from the remnant disk strikes the star along magnetic field lines, rotate in and out of view as the star spins. The disk itself can partially obscure the star as clumps and warps pass through the line of sight. And the star's magnetic activity, enormously amplified compared to a mature star, produces star spots, flares, and eruptions that modulate its brightness. The magnetic field of a T Tauri star is ferocious. A typical T Tauri star has a surface magnetic field strength of 1 to 3 kilogauss, roughly 1,000 times stronger than the sun's average field. This intense magnetism drives powerful flares, coronal mass ejections, and stellar winds that would dwarf anything our sun produces today. X-ray observations by the Chandra Space Telescope have shown that T Tauri stars regularly produce flares millions of times more energetic than the largest solar flares on record. Despite this magnetic fury, the T Tauri star continues to contract. Slowly, imperceptibly, it shrinks. Its surface temperature rises. Its core temperature climbs. The star is on a path called the Hayashi track, a well-defined trajectory on a diagram of luminosity versus temperature that describes how a contracting protostar evolves before reaching the main sequence. The star moves along this track over millions of years, dimming and warming as it contracts, gradually approaching the conditions that will allow hydrogen fusion to begin. For the first portion of the Hayashi track, the star is fully convective. Its interior is stirred from top to bottom by enormous convective cells, like a pot of water heated from below. Energy generated deep inside the star is carried outward by these roiling currents, reaching the surface and radiating into space. The surface temperature of a T Tauri star during this phase is typically around 3,000 to 4,000 Kelvin, giving it a warm, reddish-orange glow. As the star contracts further and its core heats up, a radiative zone begins to develop at the center, a region where energy is transported by photons rather than convection. This transition marks a shift in the star's internal structure and a change in its evolutionary path. The star leaves the Hayashi track and begins to move along the Henye track, growing hotter at roughly constant luminosity as it approaches the main sequence. The disk around a T Tauri star is thinner and more evolved than the accretion disk of a younger protostar. It is now called a protoplanetary disk, and planet formation is well underway within it. Observations by ALMA, the Atacama Large Millimeter Array in Chile, have revealed that many T Tauri disks contain concentric rings and gaps carved by forming planets sweeping up material along their orbits. The disk around HL Tauri, a T Tauri star roughly 1 million years old, shows at least 7 distinct gaps, suggesting that multiple planets may already be taking shape. The T Tauri phase is the bridge between formation and maturity. The star has stopped accreting, stopped hiding, stopped launching jets. But it has not yet begun to fuse hydrogen. It exists in a prolonged adolescence, visible, active, variable, and slowly contracting toward the moment when its core will finally become hot and dense enough to sustain nuclear reactions. That moment, the ignition of hydrogen fusion, is not dramatic. There is no explosion, no flash, no sudden change. The core temperature climbs past 10 million Kelvin, and the proton-proton chain begins. 2 hydrogen nuclei collide and fuse, releasing a tiny burst of energy, then another pair, then another. The rate of fusion increases as the temperature rises, and gradually, over thousands of years, the energy output from fusion matches the energy being radiated from the surface. The star reaches hydrostatic equilibrium. The outward push of radiation pressure balances the inward pull of gravity, and contraction stops. The star has been born. But this moment, this quiet ignition, this gentle crossing of a threshold, comes 10 to 50 million years after the original molecular cloud core first began to collapse. The star has no memory of the cold, dark cloud it came from. It has no record of the millions of years it spent falling, warming, glowing, contracting. It simply burns steadily and calmly as if it has always been there. And it will continue to burn for billions of years, far longer than it took to be born. The competition, why not all gas becomes stars? One of the most surprising facts about star formation is how inefficient it is. The molecular clouds that give birth to stars are enormous, containing enough gas to build thousands or millions of stars. And yet, in any given cloud, only a tiny fraction of the available gas is ever converted into stars. The rest is dispersed, blown away, heated, or simply left behind as the cloud dissipates over millions of years. The efficiency of star formation in a typical molecular cloud is roughly 1 to 5%. That means for every 100 solar masses of gas in a cloud, only 1 to 5 solar masses end up inside stars. The remaining 95 to 99% is returned to interstellar space, where it may eventually participate in another round of cloud formation and collapse millions or billions of years later. This inefficiency is not a failure of the process, it is a fundamental feature of it, governed by the same physics that makes star formation so slow. Several forces conspire to prevent most of the gas in a cloud from ever reaching a protostar. The first and most pervasive is turbulence. Molecular clouds are not calm, still reservoirs of gas. They are churning, roiling, chaotic environments where supersonic currents of gas collide, compress, and rebound. This turbulence provides support against gravitational collapse on the largest scales, preventing the entire cloud from contracting at once. Only the densest, most sheltered pockets, the cores, are calm enough for gravity to take hold. The rest of the cloud is too turbulent to settle down. The second force is magnetic pressure. Molecular clouds are threaded with magnetic fields that permeate the gas and dust. These fields provide an additional source of support against collapse, particularly in the lower density regions between cores. Magnetic pressure does not prevent collapse entirely, but it slows it dramatically and limits the rate at which gas can accumulate onto forming protostars. In strongly magnetized regions, gas must slowly drift across field lines through a process called ambipolar diffusion, a leakage so gradual that it adds millions of years to the formation timescale. The third force is feedback from the stars themselves. As soon as the first protostars in a cloud begin to form, they start fighting back against the cloud that created them. Protostellar jets inject energy and momentum into the surrounding gas, stirring up turbulence and disrupting neighboring cores. As the protostars evolve into T Tauri stars and eventually reach the main sequence, their ultraviolet radiation heats and ionizes the surrounding gas, creating expanding bubbles of hot plasma that push the cold gas outward. The most massive stars are the most destructive. A single O-type star, the rarest and most luminous class, can ionize and disperse an entire section of a molecular cloud within a few 100,000 years of reaching the main sequence. The Orion Nebula is a vivid example. The bright, glowing gas visible in photographs is a region of the molecular cloud that has been ionized and heated by a handful of massive young stars at its center. The cold gas behind the nebula is being eaten away by the radiation, and within a few million years, the entire visible region will be dispersed. This feedback creates a paradox. Stars are born from molecular clouds, but in being born, they destroy the clouds that created them. The process of star formation is self-limiting. Each generation of stars erodes the raw material available for the next generation, ensuring that only a small fraction of the cloud's mass is ever converted into stars before the cloud is dispersed. The timescale of cloud dispersal adds another layer to the slowness of the process. A typical molecular cloud survives for roughly 10 to 30 million years before being disrupted by internal star formation, external gravitational perturbations, or both. In that time, it converts only a few percent of its mass into stars. The stars that form are permanent. They will burn for millions to trillions of years. But the cloud itself is temporary, a brief concentration of gas that flickers into existence, produces a generation of stars, and then dissolves back into the diffuse interstellar medium. Some of the gas that escapes a dispersing cloud will cool, drift, and eventually accumulate into a new molecular cloud somewhere else in the galaxy, millions of years later. That new cloud will begin the process again, collapsing, fragmenting, forming cores, building protostars. The cycle of cloud formation, star formation, and cloud dispersal repeats endlessly across the Milky Way, on a timescale of roughly 50 to 100 million years per cycle. It has been repeating for over 13 billion years, since the first molecular clouds condensed from the primordial gas of the young universe. This means that the gas in any molecular cloud you observe today has likely been through this cycle many times before. The hydrogen atoms falling onto a protostar in the Orion Nebula right now may have been part of a molecular cloud 2 billion years ago, then dispersed, then reformed, then dispersed again, cycling through generations of clouds and stars, like water through an endlessly slow hydrological cycle. The inefficiency of star formation is, in its own way, a form of conservation. By converting only a small fraction of its gas into stars, the galaxy ensures that the raw material for star formation is never exhausted. If molecular clouds were perfectly efficient, if every atom of gas became part of a star, the Milky Way would have burned through its entire gas supply billions of years ago, and star formation would have ceased. Instead, the inefficiency stretches the process out across cosmic time, ensuring that new stars are still being born today, 13.5 billion years after the galaxy formed. It is a strange and beautiful thought. The wastefulness of star formation is precisely what allows it to continue. The slowness, the inefficiency, the vast amounts of gas that never become stars, these are not failures. They are the universe's way of ensuring that the process can go on and on and on for as long as there is gas to work with. Time scales by mass, the fastest and slowest births. Not all stars are born at the same pace. The time it takes to form a star depends critically on one factor: mass. The more massive the star, the faster it forms. The less massive, the slower. This relationship is one of the most important and counterintuitive aspects of star formation, and it spans an extraordinary range of timescales. The most massive stars known, O-type stars with masses 30 to 100 times that of the Sun, complete their formation in as little as 100,000 to a few 100,000 years. These are the sprinters of the stellar world. They collapse quickly because their enormous gravity overwhelms all resistance. They accrete material at prodigious rates, sometimes swallowing 1/100th of a solar mass per year or more. They blast through the protostellar phase, skip leisurely adolescence, and arrive on the main sequence while lower mass stars in the same cloud are still barely halfway through their collapse. An O-type star can begin fusing hydrogen in its core while it is still actively accreting material from its surroundings. This is a peculiar situation. The star has been born in the sense that it is fusing hydrogen, but it is still growing, still gathering mass. It is simultaneously a main sequence star and a protostar, blurring the boundary between formation and maturity. This overlap occurs because the formation timescale is so short that the star reaches fusion temperatures before its accretion disk has been fully consumed. At the other end of the spectrum, the lowest mass stars, red dwarfs with masses below about half that of the Sun, take the longest to form. A red dwarf with 1/10, the Sun's mass may require 100 million years to complete its contraction from protostar to stable main sequence star. 100 million years. In that time, the Earth orbits the Sun 100 million times. The continents drift measurably across the planet's surface. Entire species evolve, diversify, and go extinct. The reason low-mass stars form so slowly is twofold. First, their weaker gravity means the initial collapse of the cloud core is more gradual. The free-fall time for a low-density core is longer, the accretion rate is lower, and the overall process simply takes more time. Second, and more importantly, the contraction from bloated protostar to compact main sequence star is governed by the Kelvin-Helmholtz timescale, the time it takes for the star to radiate away its gravitational energy. For a low-mass star, this timescale is enormously long because the star's luminosity is very low. It radiates energy so slowly that shrinking to its final size takes tens of millions of years. Our Sun sits in the middle of this range. A star of one solar mass takes roughly 10 to 50 million years to form, depending on how you define the starting and ending points. The initial collapse of the cloud core takes a few 100,000 years. The protostellar accretion phase lasts 1 to 2 million years. The T Tauri contraction phase lasts another 10 to 30 million years. And then, quietly, hydrogen fusion begins. The Sun's formation time is a compromise. Fast enough to seem swift by red dwarf standards, slow enough to seem glacial by O-star standards. There is a profound irony in the relationship between formation time and lifespan. The most massive stars, which form the fastest, also die the fastest. An O-type star that takes only a few 100,000 years to form will exhaust its hydrogen fuel in just a few million years, burning bright and brief before exploding as a supernova. A red dwarf that takes 100 million years to form will burn steadily for trillions of years, far longer than the current age of the universe. The universe's most patient births produce its most enduring creations. The stars that take the longest to be born are the ones that will outlast everything else, every galaxy collision, every cosmic expansion, every other star in the sky. The red dwarfs forming right now in nearby molecular clouds, slowly and invisibly, will still be burning when the universe is 100 times its current age. Their patience in formation is matched by their patience in burning. They are in no hurry to be born, and they will be in no hurry to die. Between these extremes lies a smooth continuum. A star twice the Sun's mass forms roughly twice as fast and lives roughly 1/8 as long. A star half the Sun's mass forms roughly twice as slowly and lives roughly 8 times as long. The relationship between mass, formation time, and lifespan follows mathematical curves that have been worked out in detail by stellar evolution models, and the predictions match observations remarkably well. These timescales mean that within a single molecular cloud, stars of different masses are at wildly different stages of their formation at any given moment. The most massive stars may have already reached the main sequence and begun to disperse the cloud with their radiation, while the least massive stars are still in the early stages of protostellar accretion. A snapshot of a star-forming region captures this spread beautifully. Massive, luminous stars blazing alongside deeply embedded, barely visible protostars that will not emerge for millions of years. The Orion Nebula cluster contains this full spread. At its center, the trapezium stars, 4 massive O and B-type stars, have already reached the main sequence and are flooding the nebula with ultraviolet radiation. Meanwhile, hundreds of lower-mass stars in the surrounding region are still in the T Tauri phase, surrounded by protoplanetary disks still contracting toward their own main sequence configurations. And deeper inside the molecular cloud behind the visible nebula, dozens of Class 0 and Class 1 protostars are still in the earliest stages of accretion, invisible in optical light, known only from their faint infrared signatures. All of these objects, the blazing trapezium stars, the variable T Tauri stars, and the hidden protostars, were born from the same cloud, probably within a few million years of each other. But because of the mass-dependent timescale, they exist at completely different stages of development. The massive stars are already mature, the medium-mass stars are in adolescence, the low-mass stars are still in infancy, and they are all, right now, in the same cloud at the same time. It is like a family photograph that captures a grandparent, a parent, and a newborn in the same frame. Except that the grandparent and the newborn were born only a few million years apart, and the difference in their apparent ages comes not from time, but from mass. Mass determines everything in a star's life. How quickly it is born, how brightly it burns, how long it lives, and how it dies. And it all begins with how much gas happened to fall into one particular collapsing core, in one particular cloud, at one particular moment in the slow, patient history of the galaxy. Stellar nurseries, where it happens. Star formation does not occur evenly across a galaxy. It is concentrated in specific places. Molecular clouds nestled within the spiral arms, dense filaments of gas that thread between larger structures, and compact regions where conditions happen to favor collapse. These places are called stellar nurseries, and each one has its own character, its own pace, and its own population of forming stars. To understand the slowness of star formation, it helps to visit a few of these nurseries and see the process as it unfolds in real, named locations across our galaxy. The closest major stellar nursery to our solar system is the Taurus molecular cloud, roughly 470 light-years away. Taurus is a quiet nursery, one of the calmest and most orderly star-forming regions known. It contains no massive stars. Its protostars and T Tauri stars are all low to intermediate in mass, forming slowly and gently inside long, filamentary structures of cold gas. The star formation efficiency in Taurus is very low, around 1 to 2%, and the pace is unhurried. Stars here have been forming for roughly the last few million years, and the process will likely continue for several million more before the cloud disperses. Taurus is a favorite target for astronomers studying individual protostars in detail, precisely because it is so calm. Without the disruptive radiation of massive stars, the low-mass protostars in Taurus develop undisturbed, and their accretion disks survive longer. Many of the most famous protoplanetary disks have been found in Taurus, including HL Tauri, whose ALMA image of concentric rings and gaps became one of the most iconic astronomical photographs of the decade. The Ophiuchus star-forming region is another nearby nursery, roughly 460 light-years from Earth. Ophiuchus is slightly more active than Taurus, with a denser concentration of protostars and young stars. Its most prominent feature is the Rho Ophiuchi cloud complex, a beautiful, colorful region visible in wide-field photographs, where reflection nebulae, dark clouds, and emission nebulae overlap in a tapestry of interstellar gas and dust. Deep inside this complex, dozens of Class 0 and Class 1 protostars are quietly accreting, invisible in optical light, but glowing in the infrared. Ophiuchus is notable for its filamentary structure. The gas in this region is organized into long, narrow filaments, threads of dense material that stretch for light years through the cloud. Protostars form preferentially along these filaments, particularly at the densest points where multiple filaments intersect. The Herschel Space Observatory mapped these filaments in exquisite detail, revealing that the filamentary structure is not unique to Ophiuchus, but is a universal feature of all star-forming clouds. Stars are born along threads of gas, not in shapeless blobs. Moving further out, the Orion Molecular Cloud Complex is the nearest region of truly massive star formation. Located roughly 1,340 light-years from Earth, the Orion Complex contains enough gas to form tens of thousands of stars, and it is currently doing exactly that. The most famous part of this complex is the Orion Nebula, the bright, visible region surrounding the trapezium cluster. But this represents only a tiny fraction of the total cloud. Behind the visible nebula lies a vast, cold, dark molecular cloud stretching across several degrees of sky, riddled with protostars at every stage of development. The Orion Nebula itself is a window into the cloud, a cavity carved by the intense ultraviolet radiation of the trapezium stars. This radiation has ionized and heated the gas facing us, creating the glowing nebula, while the cold molecular gas behind it remains dark and undisturbed. Protostars on the illuminated side of the cloud are exposed, their disks and jets visible in extraordinary detail. Protostars on the dark side remain hidden, known only from infrared and radio observations. The Hubble Space Telescope captured some of its most famous images in the Orion Nebula, including the proplyds, small, dark silhouettes of protoplanetary disks seen against the bright background of the nebula. These proplyds are being eroded by the ultraviolet radiation of the trapezium stars, their outer edges glowing as the radiation strips material away. The disks are being destroyed even as the planets within them are still trying to form. It is a dramatic illustration of the competition between star formation and the feedback that works to shut it down. The Eagle Nebula, roughly 7,000 light-years away in the constellation Serpens, contains one of the most recognizable structures in astronomy, the Pillars of Creation. These towering columns of cold gas and dust, imaged famously by Hubble in 1995 and again by JWST in 2022, are dense regions within a larger cloud that have resisted the ionizing radiation of nearby massive stars. The pillars are actively forming stars. Protostars have been detected at their tips, emerging from the compressed gas like seeds sprouting at the edge of a retreating glacier. The JWST image of the Pillars of Creation revealed dozens of protostars that were invisible in Hubble's optical images. Many appear as bright red points embedded within the pillars, surrounded by diffuse infrared emission from heated dust. Some are so young that they are still in the Class 0 phase, deeply embedded, barely concentrated, at the very beginning of a journey that will take millions of years. They are newborns in a nursery that is being slowly dismantled around them. The Carina Nebula, one of the largest and most active star-forming regions in the Milky Way, lies roughly 7,600 light-years from Earth. It contains some of the most massive and luminous stars known, including Eta Carinae, a hypergiant star that has already shed enormous amounts of mass and may be approaching the end of its life. The Carina Nebula is simultaneously creating and destroying, forming new stars in its dense molecular pillars, while the radiation from its existing massive stars eats away at the cloud from within. JWST's first deep field image of the Carina Nebula, released in July 2022, revealed what scientists called the cosmic cliffs, a wall of gas and dust at the edge of a cavity carved by stellar radiation. Along the cliffs, dozens of previously unseen protostars were detected, their jets punching through the gas in narrow, luminous spears. Some of these jets had never been observed before at any wavelength. The image captured a star-forming region in the act of being transformed, young stars emerging even as the cloud around them was being sculpted and eroded by the stars that came before. The Tarantula Nebula, located not in our galaxy but in the large Magellanic Cloud, a satellite galaxy roughly 160,000 light-years away, is the most vigorous star-forming region in the entire local group of galaxies. It contains thousands of massive young stars, including some of the most massive stars ever observed, with masses exceeding 100 times that of the Sun. The star formation rate in the Tarantula Nebula is so high that if it were located at the distance of the Orion Nebula, it would cast shadows on the ground at night. Despite its intensity, even the Tarantula Nebula operates on the same fundamental timescales. Its protostars still take hundreds of thousands of years to accrete their mass. Its T Tauri stars still take millions of years to contract. The difference is not speed, but scale. More gas, more cores collapsing simultaneously, more stars being built in parallel. The individual process is just as slow. The factory is simply bigger. Each of these nurseries, Taurus, Ophiuchus, Orion, the Eagle Nebula, Carina, the Tarantula, is a different expression of the same underlying physics. Gravity collapses gas. Angular momentum forms disks. Magnetic fields channel jets. Radiation and winds provide feedback. And the whole process unfolds across millions of years, in every case without exception. If you step outside on a clear night and look toward the constellation Orion, you are looking at a place where stars are being born right now. The light from the nebula carries information about protostars that have been collapsing for hundreds of thousands of years. By the time that light left the cloud, those protostars had already been falling for longer than any human civilization has existed. And by the time the light reaches your eyes, those protostars have fallen for another 1,340 years. A blink, in their terms, barely worth noticing. The triggers. What starts the clock? A molecular cloud can exist for millions of years in a state of approximate equilibrium, with gravity balanced by turbulence, magnetic fields, and thermal pressure. During this time, it drifts through the galaxy, slowly cooling, slowly evolving, but not actively forming stars. The clock of star formation does not start automatically. Something must disturb the balance. Something must push a region of the cloud past the threshold where gravity wins and collapse becomes inevitable. The most dramatic trigger is a supernova shockwave. When a massive star reaches the end of its life and explodes, the blast wave expands outward at thousands of kilometers per second, sweeping up interstellar gas and compressing it into dense shells. If this shockwave encounters a molecular cloud, it can compress the cloud's gas enough to push previously stable regions past the critical density for collapse. New cores form in the compressed layer, and within a few 100,000 years, new protostars begin to appear. This mechanism creates a poetic chain of causality. A star is born from a cloud, lives for a few million years, explodes as a supernova, and its death triggers the formation of new stars in a neighboring cloud. The new stars live, die, and trigger still more star formation. Generation after generation, stars beget stars through the shock waves of their own deaths. Our sun may owe its existence to a supernova that exploded nearby roughly 4.5 billion years ago. A star that is long gone, whose name we will never know, but whose death set in motion the collapse that led to our solar system. Evidence for supernova-triggered star formation comes from short-lived radioactive isotopes found in meteorites, remnants of the solar system's earliest moments. Aluminum-26 and iron-60, both produced in supernovae, have been detected in primitive meteorites at abundances that suggest a supernova exploded within a few light years of the nascent solar system just before or during its formation. The shock wave may have compressed the gas that became our sun. The heavy elements scattered by the explosion were incorporated into the solar nebula, and some of them ended up inside the rocky planet where you are lying right now, listening to this. Another powerful trigger is the spiral arm of a galaxy. The Milky Way has several spiral arms, large-scale density waves that rotate through the galactic disk. As a molecular cloud enters a spiral arm, it encounters a region of higher density where gas is compressed by the gravitational potential of the arm. This compression can tip previously stable clouds into collapse, triggering a burst of star formation along the leading edge of the arm. This is why spiral galaxies are so visually striking. The bright, blue, luminous regions that trace out the spiral pattern are not permanent structures. They are waves of star formation, moving through the disk like ripples on a pond. The massive, short-lived stars that form in these waves are blue and bright, illuminating the spiral arms. By the time the gas has passed through the arm and emerged on the other side, the massive stars have already died, and the surviving lower mass stars have drifted away, blending into the general stellar population. The spiral arms are not arms at all. They are standing waves of star formation, and the stars they create are merely passing through. Cloud-cloud collisions provide another trigger. When two molecular clouds happen to collide, drifting together at speeds of a few kilometers per second as they orbit the galactic center, the collision compresses gas at the interface, creating a dense layer where new cores can form. These collisions are relatively common in the inner regions of galaxies, where clouds are more numerous and their orbits more crowded. The resulting burst of star formation can produce a cluster of stars along the collision boundary. On smaller scales, the radiation and winds from existing massive stars can trigger new star formation in a process called collect and collapse. As an expanding bubble of ionized gas, powered by a young O-type star, sweeps up the surrounding molecular gas, the accumulated material at the bubble's edge can become dense enough to fragment and collapse. New stars form in the compressed shell, ringing the original massive star like smaller flowers surrounding a larger bloom. This process has been observed in numerous star-forming regions, creating distinctive patterns of age-graded star formation. The oldest stars at the center, the youngest at the expanding periphery. Even the slow drift of gas along magnetic field lines can serve as a trigger. In regions where the magnetic field is strong and the gas is weakly ionized, neutral gas can slowly slip past the ions that are tied to the magnetic field, a process called ambipolar diffusion. Over millions of years, this slow leakage allows the neutral gas to concentrate at the center of a cloud core, gradually increasing the density until gravity takes over. Ambipolar diffusion is the quietest and slowest of all triggers. It requires no external event, no shock wave, no collision. It is simply gravity and magnetism engaging in a tug-of-war so slow that millions of years pass before a winner emerges. What connects all of these triggers is their relationship to time. A supernova shock wave arrives and passes in thousands of years, but the star formation it initiates takes millions. A spiral arm passage compresses gas over a few million years, but the stars produced continue forming for tens of millions. A cloud collision lasts for a few 100,000 years, but the protostars it creates are still accreting long after the collision is over. The trigger is always brief compared to the process it sets in motion. Star formation is ignited quickly and unfolds slowly, like a match striking a candle that burns for years. And in many cases, the trigger itself was set in motion by a previous round of star formation. The supernova that compressed the cloud was a star that formed from an earlier cloud, triggered by an even earlier supernova, triggered by a still earlier event. The chain stretches backward through cosmic time, link by link, all the way to the first stars that formed from primordial gas in the young universe. Every star being born today is the latest link in a chain of triggering events that spans 13 billion years. Deep time comparisons, sitting with the numbers. Sometimes the most useful thing to do with a number is to simply sit with it. Not to explain it, not to contextualize it with clever analogies, but to let it exist in your mind and feel its weight. The numbers that describe star formation are so large that they resist comprehension, and perhaps the most honest response is to acknowledge that resistance and sit with the numbers anyway. 10 million years. That is a conservative estimate for the time it takes a sun-like star to form, from the first shiver of gravitational collapse to the ignition of hydrogen fusion. 10 million years. The oldest known human-made structure, the stone walls of Göbekli Tepe in southeastern Turkey, is roughly 11,000 years old. If you stacked the entire history of human construction from Göbekli Tepe to the skyscrapers of today, end to end, you would need to repeat that stack more than 900 times to span the formation time of a single sun-like star. The entire Holocene epoch, the geological period that encompasses all of human civilization, agriculture, writing, cities, empires, science, and everything you have ever known or read about, is approximately 11,700 years long. Star formation takes roughly 850 Holocene epochs. 1 million years ago, the species Homo erectus walked the Earth. There were no modern humans. The ice ages were cycling. The Mediterranean Sea looked roughly the same. The continents were in approximately their current positions. 1 million years is a span of time that contains the entire evolutionary trajectory of our species and more. Star formation takes 10 of those. 100 million years ago, dinosaurs dominated every continent. The Atlantic Ocean was significantly narrower. India was an island drifting northward toward Asia. Flowering plants were just beginning to diversify. The world was unrecognizable. The slowest stars to form, the smallest red dwarfs, take this long to complete their journey from collapsing cloud to stable fusion. If you could somehow watch a molecular cloud begin to form a sun-like star, and if you had the patience of a geological epoch, you would still not see it finish. You would need to watch for the equivalent of the entire Cenozoic era, the entire age of mammals from the extinction of the dinosaurs to the present, to witness the slowest stages of the process. And even then, only if the star were sun-like. A red dwarf would require you to watch longer still. Consider this comparison. Light travels at roughly 300,000 kilometers per second. In 1 year, it covers about 9.46 trillion kilometers. In 10 million years, the formation time of a sun-like star, light travels roughly 94.6 quadrillion kilometers. That distance, expressed in light years, is of course 10 million light years. It is enough to cross the local group of galaxies, the cluster of galaxies that includes the Milky Way and Andromeda, roughly twice over. While a star is being born, light has enough time to travel to a neighboring galaxy and back. Or consider the number of heartbeats. A human heart beats roughly once per second, or about 31.5 million times per year. In 10 million years, a human heart, if it could somehow beat that long, would beat roughly 315 trillion times. 315 trillion heartbeats is the formation time of a sun-like star, measured in the rhythm of a human body. The number is so large, it ceases to function as a number and becomes something closer to a texture. A vast, featureless expanse of repetition stretching beyond any horizon. The Earth rotates once every 23 hours and 56 minutes. In 10 million years, the Earth completes roughly 3.65 billion rotations. 3.5 billion sunrises and sunsets. 3.5 billion cycles of day and night. If each sunrise were a single frame in a film, playing at 24 frames per second, the film would run for approximately 4,800 years. You could start the film when the Great Pyramid of Giza was built, and it would still be playing today. And all of that, all those sunrises, all those centuries of film, would represent the time it takes to build one star. These numbers do not become easier to understand with repetition. They do not yield to familiarity. They exist at a scale that the human mind was never evolved to grasp, and the honest response is to hold them gently and let them remain strange. The slowness of star formation is not a problem to be solved or a puzzle to be decoded. It is simply the pace at which the universe builds its most fundamental objects. And that pace is, by any human measure, incomprehensibly slow. There is a peculiar peace in that incomprehensibility. The universe is not operating on a schedule that has anything to do with human concerns. It is not trying to meet a deadline, optimize a process, or achieve efficiency. It is simply following the laws of physics, which happen to require millions of years to turn a cold, dark cloud of gas into a burning star. The laws do not care how long it takes. They do not experience impatience. They simply operate, and the star forms when the star is ready. And when it does form, when fusion finally ignites and the star begins to burn, the star has no sense of the time that has passed. It does not know that it took 10 million years, or 50 million, or 100 million. It simply burns, steadily, calmly, patiently, as if it has always been there, as if the waiting were nothing at all. Multiple births, stars born together. Stars are rarely born alone. The same molecular cloud that produces one star typically produces dozens, hundreds, or even thousands, all forming within a few million years of each other. This is because the conditions that trigger collapse in one part of a cloud, a shock wave, a density enhancement, a convergence of filaments, tend to affect a wide area, initiating collapse in many cores simultaneously or in rapid succession. The result is that most stars are born as members of groups. These groups range from small, loose associations of a few dozen stars to dense, gravitationally bound clusters containing hundreds of thousands. The group a star is born into shapes its early environment, its disk evolution, and, in some cases, the kind of planetary system it can form. The simplest form of multiple birth is the binary or multiple star system. When a collapsing cloud core has enough angular momentum, it can fragment into two or more pieces, each of which collapses independently to form its own protostar. The resulting stars orbit each other, bound by gravity, and may spend their entire lives as a pair. Surveys of nearby stars suggest that roughly half of all sun-like stars are members of binary or multiple systems. For the most massive stars, the fraction is even higher. Some estimates place it above 70%. Binary formation happens early and fast during the initial fragmentation of the collapsing core. The separation between the two fragments is determined by the core's size and angular momentum, and it can range from a few astronomical units, close enough that the two protostars share a single accretion disk, to thousands of astronomical units, where the two stars develop essentially independently. Wide binaries may not even realize they are related, drifting through space together with such large separations that they appear as completely unrelated stars to casual observation. Beyond binaries, stars are born in clusters. A typical embedded cluster, one still surrounded by its natal gas, contains a few hundred to a few thousand stars within a region a few light years across. These clusters form over a period of roughly 1 to 3 million years, with the most massive stars forming first and the least massive forming last. The age spread within a cluster is small compared to the formation timescale of the individual stars, meaning that the cluster is essentially born as a unit, a generation of stars produced by the same cloud at roughly the same time. The Pleiades, visible to the naked eye in the constellation Taurus, are a young open cluster roughly 100 million years old. They have long since dispersed their natal gas and emerged as a group of bright, blue-white stars accompanied by hundreds of fainter members. The Pleiades formed together in the same molecular cloud and have been drifting through space as a group ever since. They are siblings, born from the same material at the same time in the same place. Over time, open clusters gradually dissolve. The gravitational interactions between stars, combined with tidal forces from the galaxy, slowly strip members away from the cluster's edge. Most open clusters dissolve completely within a few hundred million to a billion years, releasing their stars into the general galactic population. Our sun was almost certainly born in such a cluster, roughly 4.5 billion years ago, but its siblings have long since scattered across the Milky Way. They are out there somewhere, indistinguishable from the billions of other stars in the galaxy, carrying the same chemical fingerprint as our sun, but impossible to identify at a glance. In rare cases, star formation produces something more enduring: a globular cluster. Globular clusters are massive, dense, gravitationally bound collections of hundreds of thousands to millions of stars packed into a spherical region only a few tens of light years across. The Milky Way contains roughly 150 known globular clusters, most of them very old, 10 to 13 billion years, relics of an earlier epoch when the galaxy was young and gas-rich. Globular clusters represent the most extreme form of synchronized star formation. Hundreds of thousands of stars, all born within a few million years, in a single, catastrophically dense cloud. The conditions that produce them, enormous gas densities, rapid cooling, minimal feedback, were more common in the early universe and are rare today. No new globular clusters are being formed in the Milky Way at the present time. The association between star formation and clustering has a deeper significance. It means that the history of star formation in a galaxy is not a smooth, continuous process, but a series of episodes, bursts of activity in specific clouds at specific times, producing specific generations of stars. Each generation carries the chemical signature of the cloud that formed it, enriched by the deaths of all the stars that came before. By measuring the chemical abundances of stars in a cluster, astronomers can determine when and where they were born, and what the galaxy looked like at that time. This is stellar archaeology, reading the history of the galaxy and the chemistry of its stars. And it is made possible by the fact that stars are born in groups from shared material on shared timescales. If every star formed alone in isolation, the record would be hopelessly scrambled. But because they form together, in clusters and associations, the record is organized into legible chapters. The slow, patient process of star formation produces not just individual stars, but communities. And those communities, drifting apart over millions and billions of years, carry with them the memory of the cloud that made them, a cloud that no longer exists, a place that has long since dispersed into the interstellar medium, but whose legacy lives on in every star it produced. The debris left behind, planets, moons, and leftovers. Star formation does not produce only stars. It produces everything that orbits a star. Planets, moons, asteroids, comets, and the diffuse clouds of dust and ice that drift through planetary systems for billions of years. These objects are not an afterthought. They are a natural, inevitable consequence of the same process that builds the star itself. When a collapsing cloud core forms a protostar, the disk of gas and dust that surrounds it becomes the raw material for planet formation. This protoplanetary disk contains roughly 1% of the total mass of the system. The rest is in the star. But that 1% is enough to build an entire planetary system. Our solar system's planets, moons, asteroids, and comets together contain roughly 1,000th the mass of the Sun. It does not take much material to make a world. Planet formation begins while the star is still forming. Within the protoplanetary disk, tiny dust grains, the same micrometer-sized particles that existed in the original molecular cloud, begin to collide and stick together. This process, called coagulation, builds progressively larger aggregates. Dust grains become pebbles. Pebbles become rocks. Rocks become boulders. The growth is slow, driven by random collisions in the turbulent disk, and the early stages take tens of thousands of years to produce objects even a centimeter across. The journey from centimeter-sized pebbles to kilometer-sized planetesimals is one of the least understood stages in planet formation. Direct growth through collisions becomes inefficient at this size range because the collisions tend to shatter the objects rather than merge them. Several mechanisms have been proposed to bridge this gap, including the streaming instability, a process in which pebbles concentrate in dense clumps within the disk and collapse under their own gravity to form planetesimals directly. This mechanism can operate relatively quickly, producing kilometer-sized bodies within a few thousand orbital periods. Once planetesimals exist, gravity takes over. The largest planetesimals attract smaller ones through gravitational focusing, growing rapidly in a process called runaway growth. Within a few 100,000 years, the largest bodies in the disk can reach the size of Mars or larger. Protoplanets massive enough to significantly perturb the orbits of nearby material. These protoplanets continue to grow by sweeping up remaining planetesimals and gas, eventually becoming the full-sized planets of the mature system. The timescale for building a gas giant like Jupiter is constrained by the lifetime of the gas disk. The disk typically dissipates within 3 to 10 million years after the star's formation, as the gas is either accreted onto the star, blown away by stellar radiation, or incorporated into planets. A gas giant must build a solid core massive enough to gravitationally capture hydrogen and helium from the disk before the gas is gone. Models suggest this requires the core to reach roughly 10 Earth masses within the first few million years, a tight deadline by astronomical standards. Rocky planets like Earth can take longer because they do not need to capture gas from the disk. The final assembly of Earth-sized planets through giant impacts between protoplanets is thought to have taken roughly 50 to 100 million years after the formation of the Sun. The moon-forming impact, the collision between the proto-Earth and a Mars-sized body called Theia, occurred roughly 30 to 50 million years after the solar system's formation. The Earth was still being built tens of millions of years after the Sun had already settled into stable hydrogen fusion. This means that the formation of a planetary system spans a range of timescales that overlap with and extend beyond the formation of the star itself. The star finishes forming in 10 to 50 million years. The gas giant planets must form within the first few million years before the disk disperses. The rocky planets can take up to 100 million years, and the final cleanup, the clearing of leftover debris through collisions and gravitational scattering, can continue for hundreds of millions of years. The asteroids in our solar system are leftovers from this process. They are planetesimals that never managed to coalesce into a planet, primarily because Jupiter's gravity stirred the region between Mars and Jupiter too violently for accretion to proceed. The asteroid belt contains roughly 4% of the Moon's mass, a tiny remnant of the material that once filled that region of the disk. These objects have been orbiting the Sun for 4.5 billion years, essentially unchanged since the era of planet formation. They are fossils of the construction process that built our solar system. Comets are even older, in a sense. The icy bodies in the Kuiper Belt and the Oort cloud formed in the outer reaches of the protoplanetary disk, where temperatures were low enough for water, methane, and ammonia to freeze into solid ice. Many of these objects were scattered outward by gravitational interactions with the giant planets, flung into orbits that take them thousands or millions of astronomical units from the Sun. They have been drifting in the cold, dark outer reaches of the solar system since before the Earth was fully formed. Every time a comet from the Oort cloud falls inward toward the Sun and develops its glowing tail, it is delivering material from the earliest days of the solar system's construction, ice and dust that have been preserved in deep freeze for 4.5 billion years. The water in that comet may contain molecules that were part of the original molecular cloud that collapsed to form our Sun. It is a delivery from the deep past, arriving by slow post across the longest time scale imaginable. The debris left behind by star and planet formation is not waste, it is memory. The asteroids, the comets, the dust, the moons, each one carries information about the conditions that prevailed when the system was being built. By studying these objects, scientists reconstruct the history of our own origins, reading the story of how a cold, dark cloud became a star, a disk, a family of planets, and eventually a world where someone could lie in a quiet room and wonder about all of this. And all of it, every planet, every moon, every grain of asteroidal dust, was built slowly, over millions of years, from the same patient process that built the star. The universe does not rush when it builds worlds. It takes its time, and the results are, by any measure, worth the wait. There was a time when the universe contained no stars at all. For roughly 200 million years after the Big Bang, the cosmos was dark. Not the familiar darkness of a night sky, where blackness is punctuated by points of light. Absolute darkness. A darkness so complete that there were no photons of visible light being produced anywhere in the observable universe. Astronomers call this period the Cosmic Dark Ages, and it is the longest stretch of genuine lightlessness the universe has ever experienced. During the Dark Ages, the universe consisted almost entirely of hydrogen and helium, the two simplest elements produced in the first few minutes after the Big Bang through a process called primordial nucleosynthesis. There was no carbon, no oxygen, no silicon, no iron, no gold. The periodic table had only 2 entries, and without heavier elements, the physics of star formation was fundamentally different from anything that happens in the universe today. The first stars, called population 3 stars by astronomers, using a naming convention that counts backward through stellar generations, formed from this pristine, metal-free gas. Their formation was slower in some ways and faster in others compared to modern stars. The gas was simpler, containing no dust grains to help it cool. Without dust, the primary cooling mechanism was molecular hydrogen, H2, which is far less efficient at radiating away heat than the carbon monoxide and dust that cool modern molecular clouds. This meant that the first collapsing gas clouds could not cool as effectively, and they remained warmer during their collapse. Warmer gas resists compression more strongly, which means the first collapsing clouds could not fragment into as many small pieces as modern clouds do. Instead of producing hundreds of small cores that each build a modest star, the first clouds tended to collapse into a small number of very large cores. The result was that the first stars were probably massive, perhaps tens to hundreds of times the mass of our Sun, far larger on average than the stars forming in the Milky Way today. These massive first stars would have formed relatively quickly by star formation standards, perhaps in just a few 100,000 years. Their enormous gravity drove rapid accretion, and the lack of heavy elements meant there was less magnetic resistance to slow the collapse. When they ignited, they burned at ferocious temperatures, with surface temperatures exceeding 50,000 Kelvin, far hotter than our Sun's 5,800. They radiated primarily in the ultraviolet, flooding their surroundings with ionizing radiation. The first stars did not live long. A star with 100 solar masses exhausts its hydrogen fuel in roughly 2 to 3 million years, a fraction of the time a sun-like star takes to be born. These primordial giants burned through their fuel at a prodigious rate and died in spectacular explosions, supernovae that scattered their newly forged heavy elements, carbon, oxygen, silicon, iron, into the surrounding gas. For the first time, the universe contained atoms heavier than helium. The periodic table began to fill. These first supernovae were transformative. The heavy elements they released changed the chemistry of the surrounding gas permanently. Carbon and oxygen, mixed into the primordial hydrogen and helium, provided new cooling pathways. Carbon monoxide molecules formed. Dust grains condensed from the cooling ejecta. The gas could now cool more efficiently, fragment more finely, and collapse into smaller cores. The second generation of stars, population 2, could form at lower masses, on different timescales, with different fates. Population 2 stars include the oldest stars still observable today. Many are found in globular clusters and in the halo of the Milky Way, dim, ancient, metal-poor stars that have been burning for 12 to 13 billion years. Their chemical compositions tell the story of the early universe, very low in metals, enriched by only 1 or 2 generations of supernovae, formed from gas that was only slightly removed from the primordial material of the Big Bang. The transition from population 3 to population 2 to population 1, the metal-rich stars that make up most of the modern Milky Way, including our Sun, is a story of progressive enrichment. Each generation of stars lives, fuses heavier elements in its core, dies, and scatters those elements into the gas from which the next generation forms. The result is a gradual increase in the metal content of the interstellar medium over cosmic time. Our Sun, formed 4.5 billion years ago, contains roughly 2% heavy elements by mass, the accumulated legacy of billions of years of stellar nucleosynthesis. No population 3 star has ever been directly observed. They are theoretical objects, predicted by models of early universe chemistry, and confirmed indirectly by the chemical signatures of the oldest known stars. The James Webb Space Telescope was designed in part to search for evidence of these first stars, either directly, by detecting their light from the earliest epochs of the universe, or indirectly, by studying the chemical patterns in the most distant and ancient galaxies. In 2023 and 2024, JWST observed galaxies from the first few 100 million years after the Big Bang, objects so distant that their light has been traveling for over 13 billion years. Some of these galaxies appear surprisingly bright and well-formed for their age, suggesting that star formation in the early universe may have been more vigorous than previously expected. The data is still being analyzed and debated, but it is clear that the first stars left a profound mark on the universe, transforming it from a dark, featureless expanse into the structured, luminous cosmos we observe today. The first stars were the universe's experiment, the prototype built from the simplest materials under the most primitive conditions. They were massive, brief, and brilliant, and in their deaths, they planted the seeds for everything that followed: the smaller, longer-lived stars, the rocky planets, the complex chemistry, and eventually the conscious minds that would one day look back across 13 billion years and wonder how it all began. That wondering is itself a product of the chain they started. The carbon in your body was forged in a star. The oxygen you breathe was assembled in a stellar core. The iron in your blood was born in a supernova. Every atom heavier than hydrogen and helium in your body passed through at least one star, and possibly several, before finding its way into the molecular cloud that collapsed to form our sun, our planet, and eventually, you. The first stars did not know they were starting something. They simply formed, burned, and died. But the process they set in motion has not stopped since. Stars being born right now, the ongoing process. At this very moment, as you lie in whatever quiet place you have found for yourself tonight, stars are being born. Not metaphorically, not poetically, literally. Right now, in molecular clouds scattered across the Milky Way, dense cores are collapsing, protostars are accreting, T-Tauri stars are contracting, and hydrogen fusion is igniting in objects that have been forming for millions of years. The process has not stopped. It has been continuous for over 13 billion years, and it shows no sign of slowing down. The Milky Way currently forms new stars at a rate of roughly 1 to 3 solar masses per year. That might sound modest for a galaxy containing 200 to 400 billion stars, and in a sense it is. The Milky Way's most vigorous star-forming days are behind it, concentrated in the first few billion years after the galaxy assembled. But 1 to 3 solar masses per year still translates to several new stars annually, spread across the galaxy's molecular clouds. Most of this star formation is happening in the galaxy's spiral arms, where the density of gas is highest and the conditions most favorable for cloud formation and collapse. The Sagittarius arm, the Perseus arm, and the Scutum Centaurus arm are all active regions of ongoing star formation. Our solar system sits between the Sagittarius and Perseus arms in a relatively quiet interarm region, a calm neighborhood between two busy construction zones. The nearest sites of active star formation are remarkably close by galactic standards. The Taurus and Ophiuchus molecular clouds, both within 500 light-years, contain protostars in the earliest stages of development. The Orion complex, at 1300 light-years, is forming stars across the full range of masses. The Scorpius-Centaurus Association, a group of young stars roughly 400 light-years away, represents a recently completed episode of star formation, stars born from a cloud that has since dispersed, now drifting through space as a loose, aging family. Some of the protostars currently forming in these nearby clouds will outlive every structure in the universe. The smallest red dwarfs being assembled right now in the Taurus molecular cloud will still be burning trillions of years from now. Long after the sun has died, long after the Milky Way has merged with Andromeda, long after the last massive star in the universe has exploded, these tiny, faint, patient stars, currently just blobs of warm gas hidden inside dark clouds, will inherit the cosmos. Other protostars forming right now will live fast and die young. Massive protostars in the Carina Nebula and the Orion Complex are accreting material at rates that will build O-type giants, stars that will blaze for a few million years and then detonate as supernovae, seeding the next generation of molecular clouds with heavy elements. Their deaths will trigger new collapses, new protostars, new cycles of birth and destruction. The chain continues. The rate of star formation in the Milky Way will gradually decline over cosmic time. As the galaxy slowly exhausts its supply of cold gas through star formation, heating by stellar radiation, and the eventual cessation of gas infall from the intergalactic medium, fewer and fewer molecular clouds will form, and the rate of new star births will drop. Models suggest that star formation in the Milky Way will continue at a diminishing rate for several tens of billions of years before effectively ceasing. But that endpoint is unimaginably far in the future. For now, the galaxy is still an active stellar nursery. Somewhere out there, right now, a core that has been quietly collapsing for 100,000 years has just passed the threshold of opacity. Somewhere else, a protostar that began accreting 1,000,000 years ago is approaching its full mass. Somewhere else still, a T-Tauri star that has been contracting for 20 million years is about to ignite hydrogen fusion in its core for the first time. All of these events are happening simultaneously across the galaxy in an overlapping, continuous process that has been running since the universe was a few 100 million years old. You cannot see any of this from where you are. The forming stars are hidden in the dark clouds, glowing only in the infrared, observable only with space telescopes and radio arrays. But they are there. The galaxy is building new stars tonight, just as it has every night for the past 13 billion years. The construction never stops. It simply happens too slowly and too far away for anyone to notice. There is something comforting in that continuity. Whatever is happening in the world around you, whatever worries or concerns or unfinished thoughts you carry into this quiet hour, the galaxy is doing what it has always done. Slowly, patiently, inevitably, it is turning cold gas into light. It does not require your attention to do this. It does not require anyone's attention. It simply happens, as it has always happened, on a timescale so vast that the rise and fall of every human civilization is a rounding error in the process. The stars being born right now will not be finished for millions of years, and that is fine. They are in no hurry. Neither, for the moment, are you. The Patience of the Universe. Philosophical reflections on slowness. There is a tendency, deeply embedded in human thought, to associate speed with importance. The things that happen quickly capture our attention. The things that happen slowly fade into the background. We measure productivity in tasks per hour, communication in seconds of lag, technology in processing speed. The fast is valued, the slow is tolerated. Star formation inverts this hierarchy entirely. The most important creative act in the physical universe, the process that builds the engines of light, the forges of heavy elements, the anchors of planetary systems, the sources of all energy that sustains life, is also the slowest. It is not slow because it is inefficient. It is not slow because it lacks energy. It is slow because the physics of gravitational collapse, operating across interstellar distances, at molecular densities, against the resistance of pressure and magnetism, and turbulence simply requires that much time. The slowness is not a limitation. It is the mechanism. Without millions of years of gradual contraction, a collapsing cloud would never build the pressure and temperature needed to ignite fusion. Without slow accretion through a disk, the angular momentum of the infalling gas would prevent it from reaching the protostar. Without the patient clearing of the envelope by jets and radiation, the young star would remain forever hidden. Every stage of the process takes as long as it does because that is exactly how long the physics requires. There is a lesson in this, though it is not the kind of lesson that arrives with clarity and instruction. It is more like a feeling, a quiet recognition that patience is not the absence of progress. It is the form that progress takes when the work is deep and the materials are vast and the outcome is worth the wait. The universe does not rush its stars. It does not cut corners. It does not optimize for speed. It simply allows the process to unfold at its natural pace, and the result is something that burns for billions of years. Human beings have always found meaning in the stars. Long before anyone understood what they were, people looked up and felt something. Awe, perhaps, or loneliness, or belonging, knowing that each of those points of light was built over millions of years of silent, invisible work does not diminish the awe. If anything, it deepens it. The light you see when you look at a star is not just the product of nuclear fusion. It is the product of an entire epoch of patience, a long, slow, faithful commitment of gravity to its work. The philosopher Blaise Pascal once wrote that the silence of infinite spaces frightened him. But perhaps the silence is not frightening. Perhaps it is simply the sound of patience. The universe is quiet because it is working. It is dark in places because light has not yet been built there. It is cold in places because warmth is still millions of years away. The silence and the darkness and the cold are not emptiness. They are the early stages of something magnificent. Every star you have ever seen was once a patch of cold, dark gas that no one would have noticed. Every sunrise you have ever experienced began as a molecular cloud drifting through a spiral arm, unaware that it carried within it the seeds of a star, a planetary system, and a world. The process that built our sun began long before the earth existed, long before life existed, long before consciousness existed, and it unfolded with a patience so absolute that the word patience barely applies. Patience implies waiting for something. The universe was not waiting. It was simply becoming. Perhaps the deepest thing star formation teaches us is that the most extraordinary outcomes do not require extraordinary speed. They require only the steady, faithful application of simple forces, gravity, pressure, rotation, radiation, over spans of time that dwarf everything we know. The universe builds its wonders slowly, because that is the only way to build them at all, and it does not mind. It has all the time there is. What slowness teaches, the closing meditation. We have traveled a long way together tonight, from the cold, dark interior of a molecular cloud to the first faint glow of a protostar, from the slow spiral of an accretion disk to the turbulent adolescence of a T-Tauri star, from the triggers that start the clock to the planetary systems built as a byproduct, from the first stars that lit up a dark universe to the ones being born, quietly and invisibly, right now. The thread that connected all of it was time. Not the sharp, urgent time of alarm clocks and deadlines and schedules, the deep, unhurried time of gravity and gas and light years, the kind of time that makes mountains seem sudden and oceans seem brief. The kind of time that renders even the slow drift of continents into something that happens too quickly to notice. In this kind of time, 1,000,000 years is a unit of measure. not a metaphor for forever. In this kind of time, the entire human experiment, from the first stone tool to this moment, right now, is a flicker so brief that it would not register on any instrument capable of measuring star formation. We are fast, the stars are slow, and somehow, improbably, the fast emerged from the slow. The conscious arose from the patient, the curious appeared inside the calm. You are made of material that was assembled slowly. The carbon in your cells was forged in a star that took millions of years to be born and millions more to die. The oxygen you are breathing right now was built in a stellar core over epochs. The iron carrying oxygen through your blood was created in the final seconds of a supernova that ended a life spanning millions of years. You are the product of processes so slow that you can barely imagine them, and yet here you are, awake, or nearly so, in a quiet room, at the end of a day that lasted roughly 16 hours, thinking about stars. The contrast is not ironic, it is beautiful. The fast and the slow are not in competition, they are partners. The slow built the stage, the fast populated it, the slow created the conditions. The fast, life, thought, wonder, curiosity, love, arose within those conditions, like flowers in a garden that took an epoch to prepare. Right now in the Taurus molecular cloud, a dense core is collapsing. It has been collapsing for 200,000 years. It will collapse for 200,000 more before a protostar forms. That protostar will accrete for 1,000,000 years. It will contract for 10 million years. And then, quietly, hydrogen will fuse, and a new star will join the billions already burning in the galaxy. No one will notice. No telescope will record the exact moment. No headline will announce it. The star will simply be there, burning steadily, as if it has always been there. And it will keep burning for billions of years, long after every concern you carry tonight has been forgotten, long after every language spoken on earth has gone silent, long after the very concept of time has lost all meaning. But tonight, you know about it. You know that somewhere out there in the dark, the universe is building something. Slowly, patiently, without any hurry at all. And that knowledge is, in its own quiet way, a kind of companionship. You are not alone in the dark. The universe is here with you, doing what it has always done, turning nothing into something, cold into warmth, silence into light. Close your eyes if they are not already closed. Let your breathing settle into whatever rhythm feels natural. The stars will keep forming while you sleep. They do not need your attention. They do not need anyone's attention. They simply form as they have always formed across millions of years, in perfect patience, in perfect quiet. And if that thought brings you any measure of peace tonight, then carry it with you into sleep. The universe is patient, the stars are slow, and there is no rush at all. Good night from Sleep Science Chronicles. One sleepy soul at a time. The genes mass, the threshold of inevitability. There is a number at the heart of star formation. A threshold, a tipping point, a line in the physics beyond which collapse becomes inevitable. It is called the Jeans mass, named after the British physicist James Jeans, who first arrived it in 1902. The Jeans mass is the minimum mass of a region of gas that will collapse under its own gravity, given its temperature, density, and composition. If a clump of gas exceeds its Jeans mass, gravity wins. If it falls short, pressure wins, and the clump remains stable. The Jeans mass depends on temperature and density in a specific way. Higher temperatures increase it. Hotter gas resists collapse more effectively, and higher densities decrease it. Denser gas needs less total mass to collapse. For a typical molecular cloud core at 10 Kelvin, the gene's mass is roughly 1 to a few solar masses, which is why most stars that form have masses in this range. The physics of gas at 10 Kelvin, combined with the typical densities of molecular cloud cores, naturally produces objects of roughly solar mass. Our sun is not a coincidence. It is a consequence of thermodynamics. The gene's mass also explains why the first stars were so massive. In the primordial universe, without heavy elements to cool the gas efficiently, temperatures in collapsing clouds were higher, hundreds of Kelvin rather than 10. A higher temperature means a higher gene's mass, which means the smallest self-gravitating fragments were much larger. The first collapsing clouds could not fragment into small pieces because small pieces were not massive enough to collapse. Only the largest concentrations had enough gravity to overcome the thermal pressure. The result was massive stars, not by choice or chance, but by the inescapable logic of a single equation. The gene's mass is a beautiful example of how a simple physical principle, the balance between gravity and pressure, determines the properties of every star in the universe. It is a single number, derivable from first principles, and it governs the mass distribution of all stellar births across cosmic history. Change the temperature by a factor of 2, and the typical mass of a forming star changes by a factor of nearly 3. Change the density, and the threshold shifts again. The stars that fill the sky are the physical solutions to this equation, played out across billions of molecular cloud cores over 13 billion years. And the remarkable thing is that the gene's mass is not large. For a modern molecular cloud at 10 Kelvin, 1 solar mass is enough. 1 solar mass of gas, a tiny fraction of the cloud's total, is sufficient to cross the threshold and begin an irreversible collapse. The threshold is low. The commitment is total. Once the gene's mass is exceeded, the gas will collapse, a protostar will form, and eventually a star will burn. There is no going back. The line has been crossed, and the only remaining question is how long it will take, which, as we have seen, is millions of years. Insert after accretion disks and jets cluster before T Tauri stars. The Herbig-Haro menagerie. Jets frozen in time. Herbig-Haro objects are among the most photogenic features of star formation, and each one tells a story of time and motion frozen into a single image. These glowing knots and arcs of gas mark the places where protostellar jets collide with the surrounding medium, creating shock fronts that heat and ionize the gas until it glows. They are fleeting by astronomical standards. Individual knots can change visibly over just a few years, and yet they are connected to a process that spans millions of years. They are the fast heartbeat of a very slow creature. HH-34, located in the Orion molecular cloud, is one of the most symmetrical Herbig-Haro objects known. Its jets extend in nearly perfect opposition from a central protostar, with a chain of evenly spaced knots along each beam. The spacing of the knots reveals that the jet's velocity has varied over time. Each knot represents a burst of faster material, catching up to slower material ahead of it, creating a pileup that glows as the gas is compressed and heated. The pattern repeats every few hundred years, suggesting that the accretion rate onto the protostar fluctuates on similar timescales. HH-111, also in Orion, features one of the longest known protostellar jets, extending roughly 12 light-years from end to end. The jet has been active for at least 10,000 years, based on the distance traveled by its outermost knots at the measured velocity. 10,000 years of continuous jetting is a long time by human standards, but a brief episode in the star's formation. The jet phase represents perhaps 1 to 2% of the total time required to build the star. HH211, a young and deeply embedded protostellar jet in the Perseus molecular cloud, was imaged by JWST in unprecedented detail in 2023. The image revealed a series of symmetric bow shocks, curved, luminous arcs where the jet material slams into surrounding gas. The bow shocks resemble the wake of a boat moving through still water, and they trace the history of the jet's activity over the past few thousand years. Each bow shock represents a distinct ejection event, launched from the protostar's poles as accretion variability sent pulses of material streaming outward. What makes Herbig-Haro objects so valuable to astronomers is that they are visible. Most of star formation is hidden, buried in opaque clouds, radiating only in the infrared, changing too slowly to observe. But Herbig-Haro objects change fast enough to watch. By comparing images taken years or decades apart, astronomers can measure the velocities of individual knots, track their motion, and reconstruct the history of the jet that produced them. It is like reading a diary written in glowing gas, each entry separated by a few centuries. The jets themselves carry a significant amount of material, roughly 1/10 to 1/100th of the mass being accreted onto the protostar. This means that for every 100 solar masses of gas that falls onto a forming star, 1 to 10 solar masses are ejected back into the cloud through the jets. This return material stirs turbulence in the surrounding gas, injects energy, and may trigger or suppress the formation of other stars nearby. The jets are not just a byproduct of star formation. They are a feedback mechanism that regulates the process, ensuring that it remains slow and self-limiting. When the accretion phase ends and the jets shut off, the Herbig-Haro objects they created linger for a while, a few thousand years, before fading as the shocked gas cools and disperses. The glowing knots dissolve into the interstellar medium, and the jet's legacy becomes invisible. Within 10,000 years of the jet's cessation, almost no trace remains. The protostellar jets are cosmic graffiti, bright, vivid, temporary messages written across the dark walls of a molecular cloud, announcing that a star is being born inside. Insert after timescales by mass cluster before stellar nurseries. The Kelvin-Helmholtz timescale, a clock for contracting stars. There is a formula in astrophysics that captures the patience of a contracting protostar in a single expression. It is called the Kelvin-Helmholtz timescale, named after the 19th century physicists Lord Kelvin and Hermann von Helmholtz, who first used it to estimate the age of the sun, incorrectly, as it turned out, but with a calculation that remains profoundly useful. The Kelvin-Helmholtz timescale answers a simple question. How long would it take for a star to radiate away all of its gravitational energy at its current luminosity? For a star that is still contracting, still converting gravitational energy into heat and light, this timescale tells you roughly how long the contraction phase will last. It is the clock that governs the T Tauri phase, the long, slow adolescence between the end of accretion and the beginning of hydrogen fusion. For our Sun, the Kelvin-Helmholtz timescale is approximately 15 to 20 million years. This means that if the Sun were powered entirely by gravitational contraction, with no nuclear fusion, it could sustain its current luminosity for roughly 15 to 20 million years before exhausting its gravitational energy. In the 19th century, before nuclear physics was understood, this calculation led Kelvin and Helmholtz to conclude that the Sun could not be older than about 20 million years, a figure that contradicted the geological evidence for an Earth billions of years old. The contradiction was resolved only when nuclear fusion was discovered in the 20th century, revealing a far more powerful energy source that could sustain the Sun for billions of years. But for a pre-main sequence star, a T Tauri star that has not yet begun fusing hydrogen, the Kelvin-Helmholtz timescale is the relevant clock. The star contracts, converts gravitational energy into luminosity, and gradually heats its core. The Kelvin-Helmholtz timescale tells you how long this process takes. For a star of one solar mass, the Kelvin-Helmholtz contraction phase lasts roughly 10 to 30 million years, a number that agrees well with observations of T Tauri star populations in nearby star-forming regions. For a star of two solar masses, the timescale drops to roughly 3 to 5 million years. For a star of half a solar mass, it stretches to 50 million years or more. And for the smallest red dwarfs, with masses below about 1/10 of a solar mass, the Kelvin-Helmholtz timescale exceeds 100 million years. The formula itself is elegant. The timescale is proportional to the square of the star's mass, divided by the product of its radius and luminosity. Massive stars have high luminosities, which means they radiate energy quickly and contract fast. Low-mass stars have low luminosities, which means they radiate energy slowly and contract at a glacial pace. The relationship is steep. A small decrease in mass produces a disproportionately large increase in contraction time. This is why the spread of ages in a star-forming region can be so dramatic. In the Orion Nebula cluster, the most massive stars finished contracting and reached the main sequence within 1 million years of their formation. The solar mass stars are still in the T Tauri phase, 10 million years into their contraction. And the lowest mass red dwarfs in the same cluster will not reach the main sequence for another 50 to 100 million years. They will still be contracting long after the massive stars have exploded as supernovae, and the cloud that birthed them all has dispersed entirely. The Kelvin-Helmholtz timescale is not just a number. It is a measure of cosmic patience, the time the universe requires to squeeze a bloated protostar down to the compact, dense, fusion-ready object we call a star. And for the smallest, faintest, most patient stars in the galaxy, that patience extends across an interval so long that it encompasses the entire age of complex life on Earth. Insert after deep time comparisons cluster before multiple births. The Hertzsprung-Russell diagram, a map of becoming. There is a diagram in astronomy that captures the entire life story of every star, from birth to death, in a single two-dimensional plot. It is called the Hertzsprung-Russell diagram, named after the Danish astronomer Einar Hertzsprung and the American astronomer Henry Norris Russell, who independently developed it in the early 20th century. The diagram plots a star's luminosity against its surface temperature, and when you place thousands of stars on it, patterns emerge that reveal the fundamental physics of stellar structure and evolution. On the Hertzsprung-Russell diagram, mature hydrogen-fusing stars fall along a diagonal band called the main sequence, running from hot, luminous blue stars in the upper left to cool, faint red stars in the lower right. Our sun sits near the middle of this band, a yellow star of moderate temperature and moderate luminosity. The main sequence is not a physical place. It is a state of being, the state of a star that has achieved stable hydrogen fusion and reached thermal equilibrium. But before a star reaches the main sequence, it must travel there, and the path it takes across the Hertzsprung-Russell diagram during its formation is one of the most elegant illustrations of the slowness of stellar birth. A protostar first appears on the diagram far to the right, cool and very luminous because it is large and bloated. As it contracts under gravity, it moves leftward and downward, growing hotter and dimmer. The exact path depends on the star's mass. Low-mass stars follow a nearly vertical track downward along the Hayashi track. contracting at roughly constant temperature but decreasing in luminosity as they shrink. Higher mass stars eventually develop a radiative core and shift to a more horizontal path, the Henye track, growing hotter, at roughly constant luminosity. The journey from the upper right of the diagram to the main sequence takes millions to hundreds of millions of years, depending on mass. A 5 solar mass star crosses the diagram in roughly 1 million years. A 1 solar mass star takes roughly 20 million years. A 1/10 solar mass red dwarf takes over 100 million years. Each star traces its own slow arc across the diagram, converging on the main sequence from a unique starting position. When astronomers observe a star-forming region and plot all of its young stars on a Hertzsprung-Russell diagram, the result is a snapshot of stars at different stages of their pre-main sequence journey. The most massive stars have already arrived at the main sequence. The intermediate mass stars are partway along their tracks. The lowest mass stars are still high on the Hayashi track, bloated and slowly contracting. The diagram becomes a map of becoming, a visual representation of the different speeds at which stars of different masses travel from birth to maturity. By comparing the positions of young stars on the diagram with theoretical evolutionary tracks calculated from models of stellar structure and contraction, astronomers can estimate the ages of individual stars. This technique has been used to date the populations of dozens of nearby star-forming regions, confirming that star formation in a single cloud spans a range of roughly 1 to 5 million years, with the most massive stars forming first and the least massive forming last. The Hertzsprung-Russell diagram is, in its own way, a portrait of patience. Every star on the main sequence arrived there by traveling slowly across the diagram, following a path dictated by its mass and the laws of physics. The main sequence is not where stars start. It is where they arrive after millions of years of quiet, invisible work. The stars you see in the night sky, steady, calm, apparently permanent, are all stars that have completed their journey. The ones still traveling are hidden in clouds, invisible to the eye, slowly making their way toward the place where they will spend most of their lives. Insert after. Stars being born right now. Cluster. Before. The patience of the universe. The infrared eyes. How we learned to see the invisible. For most of human history, star formation was entirely invisible. The forming stars were hidden inside opaque clouds of dust, and the tools available to astronomers, optical telescopes sensitive only to visible light, could not penetrate the shroud. The existence of protostars was predicted theoretically long before it was confirmed observationally. Astronomers knew that stars must form somehow, but the process occurred behind a curtain that visible light could not pull aside. The first hints came in the 1940s and 1950s, when Bart Bok identified small, dark globules silhouetted against bright nebulae. Compact, round patches of darkness that he suggested might be collapsing cloud cores. These Bok globules, as they came to be known, were the first observational evidence of the earliest stages of star formation. But they could only be seen in silhouette, as shadows, not as sources. The forming stars inside them remained hidden. The breakthrough came with the development of infrared astronomy. Infrared light has longer wavelengths than visible light and can pass through dust that is opaque at shorter wavelengths. A molecular cloud that is pitch black in visible light can be nearly transparent in the mid-infrared. By building telescopes sensitive to infrared wavelengths, astronomers could finally peer inside the clouds and see what was happening within. The first infrared surveys of star-forming regions in the 1960s and 1970s revealed a hidden population of luminous sources embedded within molecular clouds, objects too cool to emit visible light but glowing brightly in the infrared. These were the first confirmed protostars. The discovery was transformative. Star formation was no longer a theoretical process. It was something astronomers could see, measure, and classify. The infrared astronomical satellite, launched in 1983, conducted the first all-sky survey in the infrared, cataloging hundreds of thousands of sources and revealing the full extent of star formation across the Milky Way. Many of the protostars it detected had never been observed at any wavelength before. IRIS showed that star formation was far more widespread than optical surveys had suggested. The galaxy was full of hidden stellar nurseries, invisible to optical telescopes, buzzing with activity at infrared wavelengths. The Spitzer Space Telescope, launched in 2003, provided the next leap in sensitivity and resolution. Spitzer surveyed all of the major nearby star-forming regions in the infrared, producing detailed censuses of protostars at every evolutionary stage. The Spitzer Legacy programs, large, systematic surveys of clouds like Orion, Taurus, Ophiuchus, Serpens, and Perseus, provided the foundation for our modern understanding of how stars form, how long each stage lasts, and how the process varies from cloud to cloud. The Herschel Space Observatory, launched in 2009, extended the infrared window to far infrared and submillimeter wavelengths, the regime where the coldest, youngest, most deeply embedded protostars emit most of their radiation. Herschel revealed the filamentary structure of molecular clouds, the distribution of dense cores within those filaments, and the initial conditions of star formation with unprecedented clarity. The Herschel-Gould Belt Survey mapped all of the major star-forming regions within 500 parsecs of the Sun, providing a complete inventory of the raw material and early stages of star formation in the solar neighborhood. The Atacama Large Millimeter Array, or ALMA, opened another window entirely. Operating at millimeter and submillimeter wavelengths, ALMA can image the cold dust and gas around protostars with angular resolution comparable to the Hubble Space Telescope. ALMA's images of protoplanetary disks, showing rings, gaps, spirals, and asymmetries, have revolutionized our understanding of planet formation. ALMA has also detected molecules in protostellar envelopes that provide chemical clocks, allowing astronomers to estimate the ages of the youngest protostars based on their molecular compositions. And now, the James Webb Space Telescope is providing the sharpest, deepest infrared views of star-forming regions ever obtained. JWST's images of the Orion Nebula, the Carina Nebula, the Pillars of Creation, and dozens of other regions have revealed protostars, jets, disks, and outflows in detail that was previously impossible. JWST is not just observing star formation, it is watching it happen, one infrared photon at a time, across a range of wavelengths that spans the entire progression from cold cloud to hot young star. Each of these telescopes, IRAS, Spitzer, Herschel, ALMA, JWST, has peeled back another layer of the curtain that hides star formation from view. Together, they have transformed a process that was once entirely theoretical into one of the most observed and studied phenomena in astrophysics. And yet, despite all of this technology, despite decades of observations and terabytes of data, no astronomer has ever watched a star form from start to finish. The process is simply too slow. Every observation is a snapshot, a single frame in a movie that runs for millions of years. The telescopes see the present moment of each protostar's formation, frozen in time. They see the cloud as it is now, the jet as it is now, the disk as it is now. They cannot see what came before, and they cannot see what comes after. They can only infer the full story by observing many different protostars at many different stages and stitching the snapshots together into a sequence. It is like trying to understand the growth of a tree by photographing 1,000 different trees and arranging the photos by size. This method works remarkably well. The sequence of star formation, from molecular cloud to dense core, to collapsing envelope, to protostar, to T Tauri star, to main sequence star, is now understood in extraordinary detail, assembled from millions of observations of thousands of objects across dozens of star-forming regions. The picture is coherent, consistent, and deeply supported by both observation and theory. But there is something humbling in the knowledge that no one has ever seen the whole thing. No one has watched a cloud begin to collapse and followed it all the way to a burning star. No one ever will. The process is too slow for any observer, any telescope, any civilization. We know the story because we have pieced it together from fragments, glimpses of a process so vast and so patient that it exceeds the lifespan of every instrument we have ever built. And perhaps that is fitting. The slowest process in the universe has taught us something about the limits of observation and the power of inference. We cannot watch a star being born, but we can understand it in detail through the accumulated work of generations of scientists, each contributing one more snapshot to the sequence. The understanding itself was built slowly over decades by thousands of people. In that sense, our comprehension of star formation mirrors the process it describes, patient, gradual, and ultimately luminous.